Today we are going to start lecturing on Module 7, which is a special type of connected graph called trees. We're going to go through some basic definitions and some properties. I will show you proof of some important and nice results about trees. But as far as your homeworks are concerned, your questions are going to be pretty basic about the properties of trees. So we are not going to talk about the intricacy of the results and their proofs, as long as I am expecting you to answer questions. So let's start with the definition of trees and what is so special about trees. What we are expecting in a discrete mathematics class when we are studying trees to help us do discrete mathematics better. What is a tree? What distinguishes trees from other types of graphs is the absence of certain paths called cycles. Recall that a path is a sequence of consecutive edges in a graph, and a circuit is a path that begins and ends at the same vertex. So essentially you can think of it's a self loop that consists of more than one edge. So for example, if I take the graph connecting four vertices, which basically gives us the shape of a rectangle, and I call these vertices, say, A, B, C, and D, then if you consider the edges that starts at A, then goes to B, then goes to C, then goes to D, and then comes back to A, that is a cycle. So we're going to define formally what is a cycle. A cycle is a circuit whose edge list contains no duplicates. Now this is not entirely true. Why it is not entirely true? Because in order to be a cycle, you have to be a self loop. So you have to start and end at the same vertex. So A, in our example, is the vertex where the loop has started and ended. So that is the only allowed vertex to be repeated in the edge levels. Other than the vertex where the loop or the cycle is best, you cannot repeat any other path. For example, so this one is a cycle, as we have talked about already. What is not a cycle in the same graph? Remember, if I had done A, B, and then from B I went to C, but then from C I went back to B, and I went back to A. In that situation, B is an intermediate vertex that has been repeated, and it's no longer a cycle. Even though this is a sequence of consecutive edges, which is going to be a circuit. So this one is going to be a circuit, but this is not going to be a cycle. So what we are expecting in our trees is that we will not see any cycle in our trees, as well as we will not see any disconnectivity. So we're going to formally define those concepts. For the time being, we have understood the difference between cycle and circuit. The simplest example of a cycle is an undirected graph is a pair of vertices with two edges connecting them. So if you think of a graph with two vertices and it's undirected, but there are two edges connecting them, so that forms a cycle. So say we call our vertices A and B, so the edges AB followed by A, so I'm taking AB in this way, that's my AB way. And then I'm coming back in the BA way, which is this one. Let me actually go ahead and use a different color so that it makes sense when I have multiple edges, how they form circuits. Because this is going to be a crucial thing in order to distinguish what is a tree and what is not a tree. So as I have said, take this path in blue and call it the first AB. And then the path from B to A, say traverse this way, and I'm going to call it B to A. So that forms a cycle, and you do not want them in your connected graph if you aren't willing to have a tree. So look for cycles, erase them from a connected graph without erasing the connectivity of the graph, and what you get is a tree. So that's formally defined tree. An undirected graph is a tree if it is connected and contains no cycles or self loops. So we're going to talk about some crucial examples that are trees and that are not trees. So let's go to our page number 2. In this example number 1, 2, 3, all three of them are connected because we can travel from any vertex to any other vertex using a path, and they don't have any self loop or a cycle. So we're going to call all three of them, example 1, 2, and 3, trees. Whereas example 4, 5, and 6 are not trees. As you can imagine, in example 4, it's a connected graph, but unfortunately, it's going to give rise to a cycle. And I'm traversing the path that is going to give rise to the cycle. Existence of the cycle is not going to make it a tree. So it has a cycle. Same thing for the next example. In 5, it is connected. It has self loops. Both this vertex and this vertex, they have self loops. That's enough for not being a tree. Also, you can think of this vertex connecting to this vertex and connecting back to the original vertex, giving you a cycle. So it is not a tree. Example number 6 is actually pretty good. This one looks so much like a tree because I don't have the problem of self loop or cycles. But what is wrong with this tree is the connectivity. We have two different trees that are not self-connected. So you have a tree, a perfect tree on the top half of the picture, and the bottom half of the picture is also a tree. But these two trees are not connected, and hence the total graph presented in this situation is not a tree. In future, we will come back to this example and define a forest. Okay, so let's talk about the examples we have just done. So we're going to go and learn a little more about existence of tree in our practical purposes. So as I have mentioned, graphs 1, 2, and 3 in figure 1.4 are all trees, while graph 4, 5, and 6 are not trees. K2, remember the complete graph with 2 vertices, is a tree. So just to remind you, the picture looks something like that. You have 2 vertices, and that is a tree. Whereas Kn for n greater or equal to 3 is never going to be a tree. So think about this situation. This is your K3, complete graph with 3 vertices, and it has a cycle, so it is not a tree, and so on and so forth. So in a loose sense, botanical trees, the trees that we actually see in nature, are all mathematical trees. There are usually no cycles in the branch structure of a botanical tree, and that's how mathematicians gave the name to this special type of graph, a tree. The structures of some chemical compounds are modeled by tree. For example, butane consists of 4 carbon molecules and 10 hydrogen molecules, where an edge between 2 molecules represents the bond between them. A bond is a force that keeps the molecules together. The same set of molecules can be linked together in a different tree structure to give us the compound isobutane. There are some compounds whose graphs are not trees. So let's see those examples in our next slide. So as we have talked about, the graph in A is the tree representing butane. Graph in B is the tree representing isobutane, whereas benzene, the benzene cycle, it doesn't have a tree structure. And as from the name and from the picture, you can see all the carbon bonds, they have double bonds, and hence it creates a cycle, and that's why the name benzene cycle, and it's no longer going to exist as a tree. It's a connected graph, but it's no longer going to exist as a tree structure in mathematics. One type of graph that is not a tree, but closely related, is the forest. So if we go back to our example where we were describing trees, the last example, remember, we have 2 trees that are not connected with each other, this situation is called a forest. It is a forest consisting of two trees. So the formal definition of a forest is an undirected graph whose components are all trees. We will now examine several conditions that are equivalent to the one that defines a tree. The following theorem will be used as a tool proving that the conditions are equivalent. So before we go to the theorem, we will do a lemma, and this lemma reads as: if G equal to V and E, the vertex set and the edge set, be an undirected graph with no self loops, and VA, VB are two vertices, if two different simple paths exist between VA and VB, then there exists a cycle in G, and hence we are not going to get a tree. So instead of going to the detailed proof, I'm going to sketch the proof in front of you. So instead of thinking about the entire graph, just think about two vertices and try to follow the argument. So you have two vertices, VA and VB, and you have two simple paths between VA and VB. So for example, I'll say this one is a path connecting VA and VB. Then I can think of a different path, and the way I'm going to do it, say the first two edges are same in both paths, but then I have a different edge getting out. You have to have at least one different edge if you want to call these two paths are different. And then it goes one more step, and then finally it goes to the final vertex, which is VB. So let me change, I called it VA, should be VB there. So this is my situation described. So what I'm going to say now, you are going to go traverse through the path till the point where you get the first time two different edges. So for example, I will start traveling from VA to VB, and I will stop for the first time where I see two different edges. Then I will pick one of these two paths. For example, say I have picked this way, and travel it till I reach VB, and then come back through the other path till I reach my first stopping point. So what I have established is the existence of a cycle. In the proof, this process has been described in an inductive fashion. So if you want to, you can actually go through and read this proof. It's going to increase your maturity of understanding trees and the generalization of proving techniques. But that's essentially what we're going to keep in mind. So the assimilation after we read this result is going to be, if you have an undirected graph with two vertices VA and VB, and there exist two simple paths, two distinct simple paths between these two vertices, then there exists a cycle, and forget about being a tree. So let's talk about our main result of this section, and this is an equivalent condition, and this is a type of result that we have never discussed in our class before. We're going to do it today. So this is theorem 1.9, and it says, find equivalent conditions to be a tree. Let G equal to VE, vertex set and edge set, be an undirected graph with no self loops, and the cardinality of the vertex set is n. So there are n vertices in the graph. Then the following conditions are equivalent. If I know that G is a tree, then I must know that for each pair of distinct vertices in V, there exists a unique simple path between them. Whereas if I know for each pair of distinct vertices in V, there exists a unique simple path between them, then I must know G is connected, and if E is an edge, then V, the edge set minus that particular edge is disconnected. So the connected graph, if you take out one edge, it becomes disconnected. If I know condition 3 is true, so if I know G is connected and E belongs to E, so E is an edge, and taking away E from the edge set makes the graph disconnected, then I must know that G contains no cycles. But by adding one edge, we will create a cycle. Then, if you know that G contains no cycles, but by adding one edge, you create a cycle, then G is connected and the number of edges in G is in -1. The number of vertices, -1. And finally, if I know that G is connected and the number of edges is 1 short the number of vertices, then G must be a tree. So it's a cycle, it's a loop. All these 5 conditions are called characteristic of a tree. So in order to define a tree, now we have 5 different properties. All we need to know, G is an undirected graph with no self-loops. If I know that much, and I know that the number of vertices in G is n, then G is a tree as long as one of 2, 3, 4 or 5 is true. All of them are necessary and sufficient condition for this undirected graph with no self-loops for becoming a tree. In order to check whether G is a tree, you can either show 2 or 3 or 4 or 5. Does not matter. On their own right, each of them are necessary and sufficient. And this is a very beautiful technique. It's called equivalence in mathematics. It's a transitive property. If we talk about relation, then this is a very, very, very nice and important property. It's a characterization of arbitrary and generalized objects in mathematics. So I'm going to actually go over this proof, and then I have a bunch of exercises where I'm going to show you how over and over I'm going to use these properties in order to check an abstract generalized structure, whether it's a tree or not. So let's start talking about the proof of this result. The way, the scheme of proving this result is exactly how I have read this result to you. We're going to assume that 1 is true, show that, then 2 is true. Then we're going to assume 2 is true, show that, then 3 is true. We're going to assume 3 is true to show that 4 is true. 4 being true will imply 5 is true. And finally, assuming 5 is true will show that 1 is true. And hence we can say that all of them are equivalent conditions. So let's start with the proof. I have actually described the strategy of proving first. So let's keep that much and let's start with the proof. The first one first. We're going to assume that 1 implies 2. So assuming that G is a tree, we're going to show that property 2 is going to be true. So assume that G is a tree and that there exists a pair of vertices between which there is either no path or there are at least 2 distinct paths. Both of these possibilities contradict the premise that G is a tree. How come? Well, if there is no path between 2 distinct vertices, then the graph is not connected. You have to be connected in order to be a tree. And if you have more than 2 distinct paths between 2 vertices, then the previous lemma has shown us that in that situation we get a cycle. And in a tree you cannot get a cycle. And hence it can't be that there are 2 vertices, distinct vertices in your graph where there is either no path between them or more than 1 path between them. So what does that say? That says that between every pair of distinct vertices in my graph, there is a unique path joining these 2 vertices. So being a tree, we have shown that the necessity of being a tree and the sufficiency of being the tree is equivalent to the condition of every pair of vertices having a unique path between them. Now let's assume that we have a graph. Forget about it is a tree. We have a graph where we have the condition that between any 2 vertex of the graph, distinct vertex, we have a unique path. And we intend to show then 3 is true. So let's remind ourselves what was property number 3. So if we go back and read property number 3, we will see that it says in our theorem that G is connected. And if E is any edge in this connected graph, then taking away E makes the graph disconnected. So we want to show that if there is a unique path between 2 distinct vertices, then if you take away any edge from your graph, the graph becomes disconnected. So let's try to check whether 2 implies 3 or not. And the proof goes this way. We now use the statement 2 as our premise. Since each pair of vertices in V are connected by exactly one path, G is connected. Because there is a connection between every 2 vertex. That is the very definition of being connected as a graph. So it is connected. Now if we select any edge E in E, it connects 2 vertices V1 and V2. And by 2, there is no simple path connecting V1 and V2 other than E. So think about any edge in your graph. There should be an initial and a terminal for this edge. And there cannot be any more edge connecting these 2 vertices. Otherwise, we have a cycle. So these are my 2 vertices and this is the edge. As I know that there is not more than one path between 2 vertices, E in this exercise is automatically that unique path between your 2 given vertices, say V1 and V2. The unique path between V1 and V2 is your edge E, and that is true for all edges. Now, for sake of understanding, let's take that edge away. Let's delete that edge from our edge set. Then there is no connection between V1 and V2. So taking away any edge from a graph where any pair of distinct vertex has a unique path connecting them is going to make that graph a disconnected graph, which proves number 3. Well, now let's assume number 3 is true. Forget about the first 2 conditions. Let's assume number 3 is true. So what do we know now? We know that G is a connected graph, and not only that, taking away a single edge, doesn't matter which edge, from this graph is going to make the graph disconnected. Using that premise, we're going to prove our property number 4. So let's see what is property number 4. It says G contains no cycles, but by adding one edge, we're going to create a cycle. So what is my premise? My premise is G is a connected graph such that taking away a single edge from this graph will make that graph disconnected. And we want to use that premise to prove that G contains no cycles. And if I add one edge in this situation, then I'm going to definitely create a cycle. So let's try to see the proof of 3 implying 4. So we'll assume that the statement 3 is true now. So there is a graph so that it is connected, and taking away any edge is going to make that graph a disconnected graph. And to prove property 4, we're going to use the indirect approach again. So since 4 is a conjunction by De Morgan's law, its negation is a disjunction. And we must consider 2 cases. First, suppose G is a cycle. So remember what we are trying to prove. We're trying to prove that G is not a cycle in this situation. So let me write them down and help you understand the conjunction disjunction situation. So you want to show G is not a cycle and we want to, the other claim is that and, so this is where the logical connective comes in, and adding one edge creates a cycle. Initially it didn't have any cycle, but if I add one edge, doesn't matter where, it's going to create a cycle. So what I generally do, identify this statement, G is not a cycle, is your P. And is your logical connective. Adding one edge will create a cycle is my Q. So because I said G for the first one, let's just say C for this one. So this statement, G is not a cycle, and adding one edge creates a cycle is G and C. So our approach is, think about the negation of that. What if this is not true? Then what happens? Then I say negation of G and C, which is what? Which is logically equivalent to negation of G or negation of C. That's De Morgan's law. So I have two different situations. First, we're going to assume that not G, so it is not that G is not a cycle. So we're going to assume double negation, so G is a cycle. And what is the other situation? Negation C is, it is not that adding an edge will create a cycle. So we'll say that no, we can add an edge and it is still not going to create a cycle. And we're going to get contradiction in either situation. So let's try to go with our notion. So first, we're going to assume that G has a cycle. Then, the deletion of any edge in the cycle keeps the graph connected, which contradicts 3. Remember, 3 told us deletion of any edge will make the graph a disconnected one. But because you have a cycle, you have more than one edge connecting at least a pair of vertices. So deleting one edge where you have those duplication of edges is not going to create any problem. As simple as that. So because I have a cycle, I must have a situation like, say, this. So this is a cycle situation. So if I delete, you pick which edge you want to delete. If you delete any one of these edges, the graph is still connected. There is a path between all 3 of these vertices. So which claims that our initial assumption is wrong, because our premise was if I delete one edge from the graph, then the graph is no longer a connected graph. But I have just shown you, if you had cycle, then deleting one edge is not going to destroy that connectivity. You are still connected. So that cannot be true. Hence, G must not have cycle. So we have taken care of the first situation. Okay, so what is the next situation that we have? The second situation that we're going to talk about now is deletion of, addition of any edge is not going to create a cycle. That's what we're assuming, negation C, that I can add an edge, but G still doesn't have a cycle. So the second case is that addition of an edge to G does not create a cycle. Then there are 2 distinct paths between the vertices that the new edge connects. So think about this situation a little bit more. So I have 2 distinct vertices in the graph in a way so that the second case, when it is saying that addition of an edge to G does not create a cycle, then there must be 2 distinct paths between the vertices that the new edge connects. So for example, I had this as one edge, and I had this as one edge, and then if I added one extra edge, then I get a cycle. So if I assume that then there are 2 distinct paths between 2 vertices that the new edge connects, by lemma 1.8 that we have talked about, a cycle can then be created, which is a contradiction because we just assumed, and I have shown you in the picture, that if you have 2 distinct paths between 2 distinct vertices and adding the edge, it must create a cycle, which is exactly what we are not assuming in this part. In this part, we assume that adding an edge is not going to create a cycle, but I have shown you that no, adding an edge is going to create a cycle. Hence, it contradicts our initial assumption. So either of negation G and negation C can be true. So what is true? G and C is true. So now we have established that if you assume 3, then it will imply 4. So let's go back to our result one more time that we are trying to prove. So we have established 1 implies 2, 2 implies 3, and 3 implies 4. So now what we will do, we'll skip 5, we will show that 4 implies 1. And there is a reason for that, which I will explain in a second. So let's see our next result. 4 implies 1. Assume that G contains no cycles and that the addition of one edge creates a cycle. All that we want to verify now, because 1 says that, then G is a tree, so we want to show that G is a tree. So all that we need to prove that G is a tree and G is connected. So if it is not connected, then select any two vertices that are not connected. If we add an edge to connect these two vertices that were not originally connected, then the fact that a cycle is going to be created implies that the second path between the two vertices can be found, which is in the original graph, which is a contradiction. So again, think about this situation one more time. So property 4 has assured us that there is no cycle. So these are my two distinct vertices, A and B, that we have assumed. And we want to show that there is a third vertex C, and A and C are not connected, because if all the vertices were connected, then the graph would be connected and hence it would be a tree. Because it doesn't have any cycle and it is connected, so it is a tree. So there must be, because I have assumed that there is no cycle, the only thing that I'm going to show that the graph is connected. If the graph is not connected, then there must be two vertices, say A and C, that are not connected. Then what I'm going to do, I'm going to just add an edge between these A and C. So this is my new edge. So I'm going to call it here. I just added a new edge, E. From the picture, it is clear that I did not create a cycle. But remember, property 4 also told you, if you add an edge, then you must have created a cycle. So what does that mean? That means in order to have this cycle, the property to be true, I must have had something already in the graph. Then adding this new edge E will make it a cycle. So you already had a connection between A and C. So our assumption was wrong, that A and C are not disconnected. If they were disconnected, then adding one edge is not going to create a cycle, which contradicts our hypothesis that adding one edge is going to create a cycle. Hence, we have proved that if 4 is true, then 1 is true. So what we have essentially done, we have shown that properties 1 through 4, all of them are equivalent. In order to be a tree, I can either show 2, 3 or 4 and get our result done. Why I didn't do 5? Because I have an exercise that I'm going to do. Literally, I'm going to write down everything from scratch and show you how 1 and 5 are also equivalent of each other. So for the time being, this is what we wanted to see in our lecture. And we're going to go ahead and start working on our exercises. So again, remember the last proof, if you're thinking like it's too abstract, you are not wrong. The proofs in mathematics, especially in graph theory, are actually pretty hard and abstract. I just want you to have a flavor of what we are doing, and it matures you in order to study graph theory and see the connection between graph theory in the world, and especially those of you who are computer science majors, what is the significance of learning graph theory and trees. Okay, so let's start talking about the exercises. The first one says that given the following vertices, draw all possible undirected trees that connect them. So the first example that we're going to do is VA, and the vertex set is given by two vertex right and left. So this is probably the easiest situation. So think about right and left being your two vertex. So say I'm going to call them this way. And this is one tree because they have to be connected, and I cannot put any more edge because then I will get a cycle. So that's the way you can do it. In practice, your answer should be there is exactly one tree connecting two vertices. But what I'm going to actually show you, there is a different format or different embedding of this tree. You can think of the left vertex in the left position and the right vertex in the right position. And according to their levelings are concerned, these two trees are different trees. But remember implicitly, very carefully, that these two trees are actually not different from each other. In fact, if you use graph isomorphism, then these two graphs as graphs, they're identical, even though their levelings are different. So that's the answer for the first question. I will do similar type of explanation for our next example, and this example is with 3 vertices plus minus and 0, and we are trying to understand how many trees are there. So let's see. So regular situation, minus is on the left, 0 is in the middle, and plus is on the right. So this is my regular situation, and that's my graph. This is one type of graph. I should have said this is 0. I'm so sorry. And then what you can do, you can just arbitrarily change the situations as we have done in the last example. So for example, you can think now that it's minus followed by plus followed by 0. Now these two graphs, they're different. How come? Think about the degree of the vertex O in the first graph. 0 has a degree of 2, whereas plus has a degree 2 in the second graph. So these are different choices. What is not different? If I had done plus 0 and minus, then this is the exact same as minus 0 plus, but the labelings are different, so I would draw it. What else is not different than the second graph? You just interchange the minus and the 0 position, but keep plus in the center with degree 2. So minus plus 0 is the same graph as, oh, I just kept them the same. So make it 0 plus minus. It is the same as minus plus 0. And the third situation that will occur is when you are going to give minus the center position and hence the degree of 2. So that's your third position. So it's a plus minus 0, or you can think of the situation where we have 0 minus plus, still the same graph but different labeling. So there are 3 possibilities up to isomorphism of graphs. As long as isomorphism is concerned, there are 3 possibilities of getting different trees with 3 vertices. Now we're going to make it 4 different vertices, and these vertices are north, south, east, west, and we will see that there are a bunch of different situations in this case. So first and foremost, I'm going to do this 4 vertices, and you start naming them north, south, east, west. As we have talked about, you can now think of the situation where you will keep north in the beginning, but instead of south, you will use east, and you will use south, and then you will use west. Now those 2 graphs are identical with each other. Why? Because in both of them, north and west has degree 1 and south and east has degree 2. So these 2 are identical situations. What else is identical with this thing? If you interchange the positions of N and W. So for example, do W, S, E, and do N, or you do W, E, S, and N. All these 4 graphs actually interpret only one situation for us. So let's talk about a different situation. As you can imagine, we will have a bunch of different examples. So now what I can do, I can say north to start, but I put south and west, and east is my outside vertex. And as you can already imagine, I will get 4 more situations of this type. So I can get north, west, south, and east. I can get east, south, west, and north, or I can get east, west, south, and north. So again, so far I have only shown you 2 different types of graphs, and what I'm going to do, I'm going to ask you to do these things on your own. Try to draw all the different situations that you can possibly imagine that will have different graphs. And as simple as you just look at the degrees of each vertex, and it's going to take you to the non-isomorphic version of the graphs, different graphs. But let's do a simple combinatorics to understand how many of these situations you can actually have. Remember, in every situation that I was drawing, you had 4 vertices, and you kind of divided them into 2 groups. One group had degree of 2, and the other group had degree of 1. So out of 4, I'm choosing 2 vertex to have degree 2. So these type of graphs, you have 4 choose 2 min. So this is the total number of graphs up to isomorphism. Don't make yourself confused that you have already drawn 8 and you are saying that there are 4 choose 2, which is 6. 4 choose 2 is going to be 6, and I'm saying that these type of graphs you will have only 6 of them. So I have drawn only 2 types here. Don't make that mistake. I have drawn only 2 types. All the blue ones and all the black ones are the same graph. And you will have a total of 6 of them. Our combinatorics knowledge has helped us understand what is the total number of graphs this way. So fill in this blank, fill in this chart. Now, are these the only graphs that we can draw with 4 vertices? The answer is no. You have different types of graph. What other types of graph we have? Well, think about the situation. North is our vertex. Then I have east, west, and south. Why this is different than the other situation? Well, in this situation, all 3 of east, west, and south has precisely 1 degree, whereas north has the degree of 3. So that's a different graph, but it's still a tree. So I have to consider them. And as usual, you can think of this situation. So let me actually use a different color to do this graph so that when you are reviewing your lecture notes, you get that idea what I have been trying to do. So again, I can keep north in the center, and I can make this one west, this one east, and this one south. As you can imagine, I can do a bunch of different cases with this type. So one of the other situations that I can think of, keeping north in the center, and the top one, instead of using south, now I can start using east, and then south and west are going to be the 2 sides, but they're still the same graph. I can do north, east, west, and south. And now, for variety, I can go ahead and say that this is north, and I can go ahead and do west up here. I can go ahead and do south and east on the 2 sides. Or the last variety of this type is going to be east, south, north, and west. So see, I have drawn already 6 different graphs which are up to isomorphism, the exact same graph. And this is the newer kind of graph. So I have more than 6 choices. The previous kind of graph I had 6 choices. This kind of graph, how many choices I'm going to have? Again, use your sense of combinatorics. Remember, in these type of graphs, you have only 1 vertex with degree 3, and the rest of the 3 vertex are going to have degree 1. So it's a simple combination problem. Out of 4, in how many ways you can select 1 vertex to have degree 3? Well, it's 4 choose 1. So I'm going to get 4 choose 1, so which is 4 total number of cases of this type of graphs. So previous kind has given me 6, this kind have given me 4. So I found so far there are total 10 different ways I can have graphs that are tree with 4 vertices. Are these all the graphs? Let's pose that question, and I'm going to let you think on your own whether you can find more graphs of this type where the graphs are trees and uses 4 vertices. So with 4 vertices, is there any other way you can make trees? The answer is no, but what I want you to think, can you use combinatorics to tell me this is exactly why I cannot have more than 10 types of different graphs up to isomorphism using 4 vertices? The answer is in combinatorics, especially in combination. So we're going to carry on. We're going to go to our next example. This example is saying, are all trees planar? Remember in module 6, we have talked about planar graphs in lesson 7. A planar graph is a graph where you can embed the graph in a way so that no edges are crossing. Are all trees planar? If they are, can you explain why? If they are not, you should be able to find a non-planar tree. The answer is yes, they're all planar. Yes, all trees are planar. Remember that theorem, which was because of Kuratowski. The theorem told us a non-planar graph must contain a subgraph that is homeomorphic to a K33 or a K5. So I'm going to answer the question similarly. I will say that if possible, let there is a tree that is non-planar, then by Kuratowski's theorem, then it must contain a subgraph homeomorphic to either K33 or K5. So let's recall what is K33. I will have 6 vertices, 3 on either sides, and the vertices on the same side are not connected with each other, but they are connected with every one on the other side. So this is my situation, and it's filled with cycles. So I'm going to say full of cycles. So you cannot have cycles in your tree. So if it is K33, then the tree is not a tree. What does that mean? Well, it's a contradiction, cannot happen. So at least I have ensured that if you have a copy of K33 as a subgraph, then you are not a tree. So you cannot have a copy, because to start with, our premise says that I'm a tree. How about K5? K5 is the complete graph with 5 vertices. So these are my 5 vertices, and I'm not done yet because this is just a cycle. I already have a cycle, but I have even worse. I have every vertex connected with every other vertex. And think about how many cycles you were thinking in this situation. So it is impossible to have K5 as a subgraph and also be a tree. So also this situation implies that the tree having a copy of K5 is not a tree because I have cycle. Hence a contradiction as well. And that tells me whatever I have pre-assumed is not true. And what I have pre-assumed, that if possible, then there is a tree which is non-planar, not going to happen. So all trees are planar trees. A simple proof, but very elegant. Okay, so we'll carry on to our next example. And this is the example that I already said that I'm going to do. This is 1 implies 5. So let's read through the statement. It says that, prove that, if G is a simple undirected graph with no self-loops, then G is a tree if and only if G is connected and the number of edges is the number of vertices minus 1. So this portion, G is a tree, is your number 1 in the equivalent condition. And if and only if G is connected and the number of edges is equal to number of vertices minus 1 is your condition 5. So we're going to finish this theorem in this part of the result. And the hint is use induction which you probably are not familiar as much, but I have used it a couple of times already, so should not be as hard. So induction is basically the mathematical technique where you show some result is true for n equal to 1. Then you assume that the result is true for n equal to k, where k is greater or equal to 1, and show the result is true for n equal to k plus 1. So our basis is where we're going to say n is equal to 1. And we will first say, so let me actually go back one step and say, let us show 1 implies 5. So I'm going to assume that, so G is a tree. And I'm going to show that the G is connected. Well, from definition of G being a tree, G is connected. So I will say from definition, G is connected. So I have already proved half of the property 5. All I have to show that the number of edges is the number of vertices minus 1. Okay, let's try to do that. And that is the portion where I'm going to use induction. So we'll say that let n be equal to 1. If I have only one vertex, what is the tree? Then the only tree is the tree with no edges. Because if you have only one vertex, what is the only possibility of an edge? Well, it's a self loop. This is the only possibility of an edge. But I cannot have a self loop because it is a simple undirected graph with no self loops. So how many edges I have? In total, the number of edges that I have is 0. Because it's a graph with no edges. So cardinality of the edge set is 0. And remember, 0 is 1 minus 1. So you can easily say that this is the cardinality of the vertex set, which is 1 minus 1. So I have established that result for n equal to 1. My induction hypothesis now is, let us assume the result is true for n equal to k, where k is greater or equal to 1. So n is the number of vertices. And I will say, then we know, because we are assuming this result is already true, then we know the edge set is n minus 1, which is equal to number of vertices minus 1. So we're going to assume that 5 is already true for n equal to k. The last step is to show that 5 is true when n is equal to k plus 1. And this is, we cannot assume, we are going to show it. So now let n is equal to k plus 1. So in this situation, we're going to finish the induction process. Number of vertices is k plus 1. Since G is a tree, by deleting one edge, we make G not connected. How do I know that? Remember the other equivalent condition. So I have to go back a couple more pages and I'm going to cite the necessary results that we had. If you look at the equivalent conditions we have already proved, there was a condition that said that if G is a tree, then G is connected, and if you delete any edge, it is no longer connected. It makes the graph a disconnected graph. So what we have now is a situation where we have a graph which is a tree and it has k plus 1 many vertices. So I'm going to say, if possible, let the number edges is so if you have k plus 1 vertex, then number of edges should be k, but I'm saying that let's let it is not k. So how much it is? We'll say that it is k plus 1 or more. So I'll say the number of edges is greater or equal to k plus 1. Okay. So if possible, let the number of edges is greater or equal to k plus 1. Now we do what? We delete one vertex. So let us delete exactly one vertex. So we have k many vertex. Since we have deleted a vertex, the associated edge will also be deleted, and I will show you in a simple picture why this is true. So think about the situation we have now. You had this vertex is the kth one set, and then you have, and I know that there will be exactly one edge because it's a tree to the k plus 1th vertex, and what I said, delete exactly one vertex and delete the associated edge. Okay, so what I have after deleting the vertex, we have a tree with, remember we deleted exactly one vertex, so now you have a tree with exactly k many vertex and the number of edges is greater or equal to k. How come? Well, before deleting this vertex, when we had k plus 1 vertex and we had more than or equal to k plus 1 edges, so remember this statement here? I'm assuming that there are greater or equal to k plus 1 many edges. In that situation, if you have deleted one vertex and the corresponding edge, the number of edges is lower by 1. So if you lower k plus 1 by 1, you get k. So now you have a tree with k vertices, but the number of edges is either k or more, which is a contradiction. How come? Because of your induction hypothesis. Remember what induction hypothesis said. Induction hypothesis said if you have a tree with k vertices, then the number of edges must be equal to k minus 1. So this is my induction hypothesis. Let us assume that the result is true for n equal to k greater or equal to 1. Then we know that number of edges is exactly 1 less than the number of vertices. Because I'm saying n equal to k, I can represent by k. So if you have k vertices in your tree, then there are k minus 1 edges. So it is a contradiction to the induction hypothesis, because now I'm saying that the number of edges is either k or more, so cannot be k minus 1. Contradiction to the induction hypothesis. Hence, number of edges in the tree with k plus 1 vertex is at least k. Why at least k? Remember, if you had k many vertices, the number of edges is k minus 1. If you increase one vertex, to maintain the connectivity, you have to increase one edge. So in a graph with k plus 1 vertices, there is at least k many edges. So at least k many edges. And we just have shown the number of edges is at least k, and at most k. It cannot be greater or equal to k plus 1. We just have proved that. So at least k and at most k means what? So exactly k. So in a graph with k plus 1 vertices, there are exactly k many edges. What does that prove for us? It proves the result for us. It says that hence number of edges is k, which is k plus 1 minus 1. Remember, k plus 1 was the number of vertices minus 1. Hence, by induction, we have proved that if you are a tree, then you are connected, and the number of vertices is exactly 1 more the number of edges, or the number of edges is exactly 1 less the number of vertices. But we still have the other way around. So now we are trying to prove that if this condition is true, so let's write that down. So this time we're going to try to show phi implies 1. Property phi implies property 1. So what we're trying to show? If there is a connected graph with no self loops, such that number of vertices minus 1 is number of edges, then it is a tree. So first and foremost, remember what is a tree. A tree is a connected graph with no self loops. So those two things we already have. It is a connected graph and it doesn't have any self loops. What else we need in a tree? That it doesn't have any cycle. So that's exactly what we're going to show, using the property that the number of edges is 1 shorter than the number of vertices. So we say, let there be 2 vertices in this graph, say VA and VB, such that there is a cycle. This is a situation what is not going to let the graph be a tree, and I'm going to show that that cannot happen. But how? So you have VA and you have VB, and I say that there is a cycle between these 2 vertices. So these are also vertices in the graph. So I'm going to just count how many edges and how many vertices are there in this cycle. So number of vertices is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this little situation of ours, there are 9 vertices in this cycle. And how many edges are there? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how about the rest of the graph? So the rest of the graph has cardinality of the vertex was n, so n minus 9, the cardinality of the rest of the graph vertices. So you had total n vertices, That's what we have assumed. Say, I'm just going to, for your sake of understanding, let's let that n was the number of vertices. I'm not sure where to put this in, but I think you are understanding what I'm trying to say. So let's just write it somewhere. Let the number of vertices is n, just to justify where the letter n comes from. Then for the rest of the graph, you have a total of n minus 9 vertex, and number of edges will be what? A number of edges already was 1 shorter than n, so it was n minus 1, but then I have counted 10 of them in my cycle. So it's n minus 11. So you have n minus 9 vertex, n minus 11 edges. So there are at least 2 vertex. Since n minus 11, the number of edges, is less than n minus 9 by 2. We have at least 2 vertex with no connection. Could be more, but at least 2, there is no connection. A contradiction, because we thought that this graph was already a connected one. So it's a contradiction as the graph is connected. And that is what is going to prove the result. Hence, we have proved there is 5 equivalent conditions. If you were a tree, then either of 2, 3, 4, and 5 is going to be a characteristic to identify yourself as a tree. So we're going to go ahead and do a couple more exercises. And these are all proof-based, but pretty simple proof-based problems. Prove that if G is equal to VE is a tree and E is an edge, then V, comma E minus E is a forest of 2 trees. So this situation is actually pretty simple. You just draw an arbitrary tree situation, whichever way you want to. It just has to be a connected graph without any self-loop and cycle. So this is my tree. And now if I take off any edge, say for example I take this edge away, so then I get 2 different trees. One is here and the other one is here. So it is a forest consisting of 2 trees. So as simple as that. Now I can use the same graph and delete a different edge. For example, this one, if I think of this situation, that was my original graph, and I decided to delete one of these edges. So what I still have is this vertex. So what you have is one tree is a tree with these vertices, and there is one other tree that has precisely one vertex. So this one is also a tree, but it's still a forest with 2 trees. The other way around, the part B is saying if V1, E1 and V2, E2 are disjoint trees and E is an edge that connects a vertex V1 to the vertex of V2, then the union of the vertex sets and the union of the edge set with this new connection is going to form a tree. So again, it's a pretty simple exercise. Think about 2 trees, whichever way you would like to, and say this is my tree on the right hand side. And now I said, if I find a new edge that connects one vertex of this tree given by V1, E1 and the tree V2, E2, then their union. So now if I think of the entire graph, it is a connected graph with no self-loops and with no circuit, and hence it's a tree. So pretty simple observation. Finally, we're going to talk about 2 nice properties about a tree. Again, characteristic property. It says prove that any tree with at least 2 vertices has at least 2 vertices of degree 1. So your tree must have 2 or more vertices, then there will be at least 2 vertices of degree 1. So let's see that. And I'm going to do it by contradiction. So I'm going to say, if possible, the number of vertex set is greater or equal to 2. And there is at most one vertex with degree 2 or less. So what did I say so far? I had to prove that in my tree I must have at least 2 vertex of degree 1. So instead I said, well, if possible, let's there be exactly 1 or less many vertex. So I said at most 1 vertex with degree 2 or less. So let's see this situation. So remember, 2 times number of edges, we did this thing in our study of graph theory in module 6, is equal to the sum of the degrees of the vertices in the graph, where V is in the vertex set. That's the result we have done. Now, degree of each of these vertex is at least 2. Degree of each of these vertex is at least 2 except 1. At most 1. So what I'm going to say? I'm going to say that I can say 2 times the number of vertices. So each of them, they have degree at least 2. So I'm going to go ahead and say that. That means the total sum of the degree is either greater or equal to 2 times V minus 1. Why minus 1? Because there could be at most 1 vertex with a degree less than 2. So minus 1. So what I have from this inequality, cardinality of the edge set times 2 is greater or equal to cardinality of the vertex set minus 1. Let's divide both sides by 2, so you get cardinality of the edge set greater or equal to cardinality of the vertex set minus 1/2. Now I know that cardinality of the edge set and the cardinality of the vertex set are whole numbers. So if you are saying one whole number is greater or equal to another whole number minus 1, then I can clearly say that, well, in this situation, the edge set must be greater than or equal to at least the vertex set. Well, what does that say? It is a contradiction. Why this is a contradiction? Because you are playing with a tree. And in a tree, the edge set is strictly less cardinality as the vertex set. So it is not even equal. Because the cardinality of the edge set is vertex set's cardinality minus 1. So this is a contradiction. Hence, what I have shown, as I have said, there is at most 1 vertex with degree 2 or less. It is not true. There should be more than 1 vertex with degree 2 or less. So there is more than 1 vertex with degree 1. That answers my question. And a similar thing we're going to do for B. B is saying, prove that if a tree is not a chain, then it has at least 3 vertices of degree 1. Okay, so not a chain means what? The tree is not a chain. So a chain situation means if you have a tree where each intermediate vertex has degree of 2 and the terminal vertices are of degree 1. So this is a chain. But I am not a chain. So remember, if you have 2 vertices, then the only tree is a chain. So this is always a chain. If you have 3 vertices, then the only tree is a chain. So because my graph, which is a tree, is not a chain, there is at least 4 vertices. That's the first situation in order to have a non-chain tree. So I at least have 4 vertices. Then we go back to A and follow the exact same argument. I want to prove that there is at least 3 vertex with degree 1. So what I will say, if possible, let there are at most, so I want 3 or more, so I will say at most 2 vertices with degree less than 2. I will say degree less than 2. Why I will say degree less than 2? Because I want to show there is at least 3 vertex with degree 1. If the vertex is not of degree 1, then it is either more than degree 2 or less than degree 2. But because it is a connected tree, you cannot have the degree 0. So not being degree 1 necessarily means your degree is either 2 or up. And I'm saying I have at most 2 of them. I'm assuming it possible that there are at most 2 vertices of degree less than 2. Then twice the number of edges, which is equal to the sum of the degree of each vertex in the graph. Now remember, each vertex has a degree 2 or up, so I can say this is equal to 2 times the cardinality of the vertex set, at least degree 2 or up, so greater than or equal to 2. But there are 2 vertices with degree less than 2, so I'm going to go ahead and say that minus 2. And then I do what? I say that hence 2 times the number of edges is greater or equal to 2 times the number of vertices minus 1. So I get, dividing both sides by 2, number of edges is greater or equal to number of vertices minus 1. So this doesn't contradict our situation completely. But remember, we can also use one other feature here. So because I said other than 2 vertices at most, every other vertex has a degree 2 or up, I will now go ahead and say, hence, at the best, the order of the edge set is strictly greater than order of the vertex minus 1, which again is a contradiction. And why I get to say that it is strictly greater than order of v minus 1? Remember, I said there are at most 2 vertex with degrees strictly less than 2. So there are at most 2 vertices with degree 1 in our hypothetical situation. So each of the other vertices must have more than degree 2, must have at least degree 2. But because you are not a chain, remember you are not a chain. What do I mean by not being a chain? You have this chain situation where the terminal vertex is already of degree 1, but the intermediate vertices are all of degree 2. So if all the intermediate vertices are of degree 2, then you get a chain situation. But it is not a chain, so you must have at least 1 vertex with degree more than 2. So I'm going to use that fact now. So we'll say, hence at the base, order of the edge set must be strictly greater than order of v minus 1, which is a contradiction, as being not chain, we must get at least 1 vertex, one intermediate vertex of degree at least 3. Because if all the intermediate vertices were of degree 2, then you got a chain. But you are not a chain, so at least 1 vertex must be of more than degree degree 2, so at least a degree of 3. What does that change in our proof? So if I go back and see the exact same proof that we have done in part A, we assume each vertex has at least a degree of 2. But I know one of them has a degree, I know for a fact, degree more than 2. So when I did all this work, I could have added 1. Or if I did not add this 1, either you add 1, or if you did not add this 1, then you could have said that, well, this is strictly greater than 2 times mu minus 2. So all these greater equal to, I could have made strict inequality. So this one is a strict inequality as well. And hence I get to say that, then order of E is strictly greater than order of V minus 1, which is not true. They must be equal to each other because your graph is a tree to start with. Hence I get to say that. Thus, there are at least 3 vertices of degree precisely 1, because assuming not so, we get a contradiction. So this is the end of our lecture, and I have mentioned it already. Your homework problems are not going to be these hypothetical, difficult proving situations. They're pretty simple. Identify what is a tree and what is not a tree, and this particular result where you're comparing the number of vertices of a graph with the number of edges of the graph in order to understand whether it's a tree or not, precisely whether the number of edges is exactly 1 short than the number of vertices to determine whether you're a tree or not, is going to be used in all your homework problems. In our next section, we're going to start talking about classes of trees and binary trees.